Hello everyone, I'm Khyati and I'm project lead for the capstone. We are a group of 5 and we are proud final year students from the prestigious Clair College. And this is our capstone project presentation overview under the guidance of our Professor Manjari Maheshwari. Our project mainly focuses on analyzing Toronto Transit Commission's bus delays, which is a common issue affecting thousands of daily commuters in Toronto. We used real-world data sets from open data portals, applied analytical techniques we learned from the data analytics program in college, and we did exploratory data analysis, visualizations, and modeling to uncover meaningful insights from the Toronto's transit system. I would like to invite my group mates to explain further what we did and how we navigated the journey of handling the delays.
Hello, myself Sankirtana. Now I'll be taking you through our interactive Tableau dashboard built from the TTC delay data. Let's take a closer look at how the dashboard brings our data to life. Let's begin with our first dashboard, a heat map showing TTC bus delays across days of the week and hours of the day. As we move across this chart, we see that each cell represents a specific time and day combination with darker shades indicating a higher frequency of delays. Here, it's clear that weekday mornings between 7 to 8 a.m. and evenings between 4 to 6 p.m. show consistent delay spikes, especially on Mondays and Thursdays. This pattern aligns with Toronto's weekday rush hours and helps us understand when delays are most likely to occur. Next, moving to dashboard 2, which gives us a delayed breakdown of delay behavior across multiple factors. At the top, we display overall metrics such as total delay incidents, average delay time, and the maximum delay recorded. Below that, the first chart on the left shows yearly and monthly delay trends, helping us observe how average delay time has shifted over the years. The second graph compares delays by direction of travel, showing that delays are more concentrated in one specific direction, possibly representing a major route bottleneck. On the top left, we analyze average delay by day of the week, and interestingly, Sunday shows the highest average delay time, likely due to limited service or operational constraints. And finally, the bottom right chart categorizes delays into long, medium, and short, with the majority falling under the long delay category, reinforcing the severity of the issue. These dashboards helped us transform raw delayed data into actionable insights, making it easier to transit operators to understand, anticipate, and respond to peak delay patterns. Thank you.
Hello, I'm Udani. For our capstone project, I worked on EDN modeling. So now I'll walk you through the steps I took during the process.
After selecting our dataset and preparing it for analysis, we conducted extensive exploratory data analysis to better understand the delay patterns. After our VDA, we tested various models to find the best fit for predicting delays. We began with the time series models like ARIMA and SARIMA to capture trends and seasonality, but they struggled with volatile patterns. In machine learning, we tried logistic regression, XGBoost, and random forest. XGBoost showed strong results, but random forest stood out for its consistency and simplicity. We also tested deep learning models such as LSTM, GRU, and MLPs. While GRU reached up to 95% accuracy, the high training cost made them less ideal for deployments. Monte Carlo simulations were also used for probabilistic forecasting, helping us understand delay uncertainties. In the end, we chose random forest, classifier, and regressor for their balanced performance and practicality. The classifier reached 96.8 accuracy, and the regressor achieved 93% among the highest across all models tested. They were also fast to train, robust against overfitting, and offered good interpretability, which made deployment through Azure ML smooth and efficient.
Hello everyone, this is Navya. In this project, I worked on Microsoft Azure Cloud Pipeline to integrate our data. Now I'll navigate you through the cloud journey.
To create a Microsoft Azure Data Factory pipeline, we need data. Further, I have created a storage account called Capstone TTC. Under this, I have created a container called caps.data. In this container, I have uploaded a dataset for our project pipeline. And next, I'm navigating to Author to create a pipeline. On this on these three dots beside the pipeline, I can see new pipeline. I'm clicking on it. And next, I'm naming this pipeline as project underscore pipeline. Sorry. To move and transform the data, we have to use copy data activities. Further, I'm dragging copy data into the canvas. And next, I'll go to the source tab. Here, I'll configure the source dataset. I have already created a linked service that connects to Azure Data Lake storage. I'm selecting a CSV file here as my source. And next, I'll go to Sync tab and I'll select the destination as in CSV. And next, we have to go to mapping and check whether the data got mapped correctly or not. Further, have to click on import schemas. So here you can see whether the data got mapped correctly or not. I feel like everything is correct here. Next, click on validate. If if it finds any error while mapping the data, you can see the error messages here. I think it's all good and we can proceed further. And next, debug. Next, publish. Publish. And that's it. We have published the pipeline and our pipeline is ready. And this is just our beginning of our cloud integration, and there is more to do. Thank you.
Hi, let me walk you through the machine learning workspace, which was created in the cloud. Machine learning workspace is nothing but a virtual environment which helps to run the models. So first, it requires a resource group on which the model has to be run. In our case, POC, TTC, bus delay. Then it's about launching the studio and then attaching the notebook in the author section, which is pretty much our code file, which we ran on the IPYNB local version of our laptops. It also has a compute instance attached within the workspace in order to have a seamless integration with the VS Code as well on the cloud. Successfully, we tested the model, we ran it on the cloud after the compute instance started, and then we could see the output as well in the last, which is our final accuracy and a prediction versus actual forecast. Due to cost constraints, we had limitations on the Azure ML workspace. We could not deploy it as a web as a service. So this was the most feasible and the fastest way to put the model on cloud. We are happy to see our first POC, that is a proof of concept around this, and improvise further as needed and as we navigate through the cloud journey. This is the final model with an accuracy of 96.8% and a regression MAE, that is the mean absolute error, of 1.89 minutes. These are the key insights from the model, and we have an overall evaluation matrix as well as a Monte Carlo simulation, which was done to see the probability distribution, along with the weather metrics, that if weather is impacting the data overall in the bus delays as well.
Thank you, Professor Manjari, for your continuous feedback during our capstone journey. And audience, we appreciate you taking time to explore the path towards an efficient TTC. On a final note, we recommend open data sharing portals, which were quite useful in gathering insights on the real world data and helped us become better data analysts. And also, last but not the least, thank you, my teammates, for their unwavering support and a willingness to learn throughout the project journey. Together, let's work towards smoother and faster journeys.